So I have this very ambiguous title here. So what I'm trying to do here is to give a very, very short introduction to Bayesian quadrature and important equivalences between Bayesian quadrature and kernel interpolation and worst case analysis. And then I'm going to use these three equivalences to prove a result about uncertainty quantification properties of Bayesian quadrature. So this result serves as some kind of an illustration of how these equivalences can be used. And well, this is based on a recent paper of ours with George Wynn, Philip Trunarp, Chris Oates, and Simo Sarkke. I'm going to present only a very small part of the paper, just for illustrative purposes. So first we'll go through some of these equivalences I talked about, and then we'll have this kind of an application of these results to uncertainty quantification. So first, a very quick introduction to Gaussian processes. So a GP, FGP, is a stochastic process on some domain omega, on some d-dimensional domain omega, which means that for each element of this probability space, the sample is a function defined on this set. And we always assume that this GP is a zero mean. So in this case, the Gaussian process is uniquely defined by its positive definite covariance kernel K, which is a function that takes two arguments. So this defines the covariance structure such that covariance of the process at any 2 points is given by the kernel. And from this and Gaussianity of the process, it follows that if you take any finite collection of capital N points, then the joint distribution of the function values at these points, or the process values at these points, is a zero mean Gaussian with covariance kernel, which is covariance matrix, which is given by this covariance kernel. And how we arrive at Bayesian quadrature is by conditioning on some data and taking an integral. So what we want to do in Bayesian quadrature is to approximate the integral of a deterministic function. So this function f will be completely deterministic and fixed, so there is no uncertainty about that anywhere in this talk. So we want to approximate the value of this integral by using evaluations of this function f at some points xn. And here I'm just taking the simplest possible integral, so there is no measure or weight function, but those could be included. I'm just skipping it to keep the notation a bit simpler here. So how this goes is that we model f as a Gaussian process FGP with covariance kernel K. Then we obtain this data D, which is just evaluations of f at these points we've chosen. And when we condition the GP on this data, we get a conditional process, which is also a GP, but it has this conditional mean function S and a conditional covariance kernel P, which have very standard algebraic forms, but those are not particularly important here. And then the Bayesian quadrature is just taking an integral of this conditional process. And because integration is a linear operation, the conditional of the integral is just a Gaussian random variable with a certain mean Q star, which can be written as a weighted sum of these function evaluations. So this Bayesian quadrature weights W star can be calculated from some using some simple linear algebra that I'm sure we'll see in later talks of this lesson. And in particular, the conditional mean is just the integral of the conditional mean function of the GP. And similarly, the conditional variance of the integral is just a double integral of the conditional covariance kernel. So then we have these two equivalences. So first of all, any given continuous positive definite kernel induces a unique reproducing kernel Hilbert space, which in this case is a certain space of continuous functions, which has associated inner product and a norm. And we can then define the worst case error of any generic quadrature rule, which has this form of being of a weighted sum of function evaluations, by taking a supremum over the unit ball of the RKHS. So this worst case error EQ is just a maximal numerical integration error for functions within the unit ball of the RKHS. And then it's quite easy to show that the Bayesian quadrature rule is actually the worst case optimal quadrature rule in this RKHS. So its weights, these W star, are the unique weights which minimize the worst case error for a quadrature rule which uses evaluations of our function at these points xn. And furthermore, you can show that this worst case error is actually equal to the conditional standard deviation given by Bayesian quadrature. So this result will be very useful later on, because it allows us to leverage a lot of stuff from information-based complexity literature. And our second equivalence is to kernel interpolation. So it's quite easy to show that the conditional mean function of Gaussian process is the kernel interpolant, which means that it's the unique function that takes this form for some coefficients alpha, such that these interpolation conditions hold. So the value of the interpolant is equal to the value of the function at our evaluation points. So there is no smoothing involved here. Furthermore, you can show that the conditional mean is the minimum norm interpolant in the RKHS, which means that the conditional mean is the RKHS function with the smallest norm, such that it satisfies these interpolation conditions. In some sense, it's kind of the smoothest possible interpolant if you want to interpret the size of the RKHS norm as telling you something about the smoothness of the function. And then we can go on to actually use these results in a answer that quantification problem. So ideally, this conditional variance is supposed to somehow quantify how uncertain we are about approximating the true integral of f by using this BQ conditional mean Qn. So if the so the GP model itself implies this kind of a credible interval where this f is the cumulative distribution function of the normal distribution. So it says that with some probability the integrals of the GP conditioned on the data are approximately standard deviation away from the BQ conditional mean. So therefore, if we are to have some kind of if our answer to the quantification by means of the conditional variance is somehow to be meaningful, we'd expect that this ratio here to be constant as we increase the number of points. It's very difficult to say anything about finite number of points. But now it needs to be recognized that our particular deterministic f does not have to have anything to do with the actual Gaussian process. So it doesn't have to be say a sample from the GP or anything like that. And the second problem is that actually the conditional variance does not depend on data. So if we here look at it, we see that there is no dependency on the function values, which is a bit problematic if the variance is supposed to tell us something about uncertainty of our approximation. Therefore, perhaps the simplest and maybe the most commonly used way to induce dependency of the variance on the function values is to use a parameterized kernel. So we take a kernel which has this scaling parameter sigma, and then we select sigma using maximum likelihood based on the data. And again, there is a well-known expression for this maximum likelihood estimate of sigma. So it is just a certain weighted inner product where we have a vector of our data values and this inverse of the kernel matrix. And if we use this scaling parameter in the GP model, then we obtain this kind of a credible interval, where now we have on the right hand side we have weighting by this scale parameter. So now we have that actually the size of the credible interval depends on our data. So what we now want to do is to analyze this kind of a standard score. So we want to analyze the ratio between the true numerical integration error for our specific deterministic function and the conditional standard deviation, which when you are doing when you have the scaling parameter, it's just a product of the scaling parameter and the kind of unscaled BQ standard deviation. And so then we say that if this ratio goes to infinity as we increase more points, as we add more points, then the BQ model is asymptotically overconfident, because this means that the standard deviation decays faster than the true error. So we think, or our model thinks, that there is less error than there actually is. And conversely, if this ratio goes to 0, then we said that we are underconfident, because in that case the true error decays faster than the standard deviation. And the main result we prove in this work is that for a number of different kernels and fixed functions, we can show that in certain cases up to logarithmic factors, that this standard score grows at most with a square root rate when your points cover your domain sufficiently well. It's of course assumed that the domain is bounded. So this says that, okay, we can become asymptotically overconfident, but we cannot become asymptotically overconfident too fast. It can only happen at a square root rate, which is perhaps reassuring, perhaps not. So here's a simple illustration of what happens. So we have some deterministic function, this dashed line here, and then we start adding data and forming the conditional distribution for the GP above and for the function above and for the integral below. So we see that the uncertainty, which is represented by this blue interval, starts to decrease, and for example, the mean of the integral starts to converge towards the true integral value. And then we'd hope that the uncertainty decays with a similar rate as the mean converges to the true integral. So to illustrate one possible result, I'm going to use Sobolev spaces. So Sobolev space of smoothness alpha can be defined as a collection of functions whose Fourier transforms f hat have a certain decay. And if this alpha is actually a multi-index, sorry, no, it shouldn't be a multi-index. It should be just an integer. In that case, this space corresponds to a space of functions having weak derivatives up to this order alpha. And the standard example where this where Sobolev spaces arise in GP regression and Bayesian quadrature is the modern kernel. So the RKHS induced by this modern kernel is a norm equivalent to a certain Sobolev space, which is related, whose smoothness is d over 2 larger than the smoothness parameter of the modern kernel. And norm equivalence means that these sets are the same as these spaces are equal as sets, and their norms are equivalent. So now we can use these equivalences I presented earlier to analyze the standard score in this Sobolev setting. So we have three quantities here in the standard score. We have this integration error, we have the maximum likelihood estimate, and then we have the unscaled conditional standard deviation. So let's first take a look at the actual integration error. So there are, in kernel interpolation and interpolation literature in general, there are several estimates for the rate of convergence of different types of interpolants when the function lives in a Sobolev space. So in particular, it can be shown that if the function is in the Sobolev space of smoothness beta, beta being not larger than alpha, and our kernel, which determines this conditional mean function here, is such that its RKHS is norm equivalent to a Sobolev space of smoothness alpha, and if our point sequence is quasi-uniform, which means that the bounded domain is covered fairly uniformly, then the conditional mean function converges to a true function with rate n2 minus beta over d in L1 norm. And we can use this kind of a bound to handle the numerator in this standard score. So we know that the numerator cannot decay slower than with this rate. But it might decay faster. That's a more difficult question. A second quantity we can analyze is this standard deviation here. So earlier we had this result that the standard deviation is the minimal worst case error in the RKHS of the kernel. And now we can use results from information-based complexity literature, which show that again, if the points are quasi-uniform and the RKHS of the kernel is norm equivalent to a Sobolev space of smoothness alpha, then this STD has a sharp rate of decay of n2 minus alpha over d. And finally, we have this maximum likelihood estimate, which can be related to the RKHS norm of the conditional mean. So it's quite easy to see that this linear algebraic expression here is actually the RKHS norm of the conditional mean. And because earlier we had this result that the conditional mean is the minimum norm interpolant in the RKHS, we have a simple upper bound for this RKHS norm in the case that our function actually happens to be an element of the RKHS. If f is not an element of the RKHS, then its RKHS norm is kind of, so to say, infinite. And informally speaking, in that case, the rate with which the RKHS norm of the interpolant, so the interpolant always exists, even if our function is not a member of the RKHS. So the rate of growth of this interpolant RKHS norm in a way quantifies how far f is from being in the RKHS. So it's using some results in the kernel interpolation literature, it's possible to show that the RKHS norm of the conditional mean cannot grow faster than with rate n2 alpha minus beta over d. So here, if beta is much smaller than alpha, so f has much less smoothness than the RKHS, then this RKHS norm might grow quite fast. But however, do note that this is just an upper bound. We do not have a similar simple lower bound, or we do have lower bounds, but they become a bit more complicated. And then we can then bring these three results together in addition to some other results that I'm not presenting here to obtain a result about slow overconfidence at most of Bayesian quadrature. So this is formulated in terms of something I like to call a Sobolev slice. So this Sobolev slice consists of functions whose Fourier transform have exactly this rate of decay. So it somehow says that these functions are precisely alpha smooth. And so our result says that if the domain is bounded and nice, so that certain results from Sobolev space theory hold, if the RKHS is normally equivalent to alpha smooth Sobolev space, if our points are quasi-uniform, if our function is in this Sobolev slice of order beta, then we have a certain rate of decay or growth for the maximum likelihood estimate, and we have this result that the standard score is growing at most square root rate up to logarithmic factors. So this can be interpreted as saying that the model can become at most slowly overconfident. And of course, we do have in this paper we do have other results. So for example, if K is any positive definite kernel, not just the Sobolev kernel, and if our function happens to be in the RKHS, then we have the same result that this standard score is of order at most order n into 1/2. And our third result is that if our function is in a certain way much smoother than the kernel, which means that our function is in a certain space defined by a Mercer integral operator, then we can actually show that the standard score goes to 0. So we have underconfidence. But none of these results are actually tight in any way. So it might be that, for example, the logarithmic factors aren't required, or that there are only a few functions in some sense for which overconfidence occurs.